Evaluate the limit with either L'Hopital's rule or previously learned methods. So in this situation, if we start off the limit by plugging in the limit value, let's see what happens. So that would give me 0 plus 1 to the 1 over 0, which would be 1 to the, well, we'll just say effectively the infinity power. But that is an indeterminate form. And it's not one of the more common ones that we know that we can use L'Hopital's rule with, the 0 over 0 or infinity over infinity, but it is an indeterminate form, which means we can use L'Hopital's rule, but we probably have to do some manipulation with this first. So the manipulation that would need to be done is invoking the use of logarithms. And the reason I'm choosing logarithms is because we have a variable up in the exponent, and in order to access that and get it out of the exponent, logarithms are key. Let me define a function that is y equals x plus 1 to the 1 over x power. And what I can do with that now is I have an equation. I can take the logarithm of both sides, and I'm going to use a natural logarithm for no particular reason. You can generally choose any base that you want, and there's really no reason not to use the natural log, I don't think. And the logarithm of the other side. Now, whenever you have a logarithm of some value raised to an exponent, you can bring that exponent out as a multiplier of the logarithm. That's just an algebraic property that logarithms possess. And it makes them very useful when you have exponents that are tricky to work with. So now I have 1 over x times the natural log of x plus 1. And at this point, I could try and see what the limit of this function is, and try to then tie that back to what the original value should be. Because if we know what this side here is supposed to be, then possibly we could apply that to this side and come up with an answer. So let's evaluate the limit as x goes to 0 of this expression here. So the natural log of x plus 1 all over x. Now, the first thing that I'll note is that if I were to plug in x equals 0, then I would have the natural log of 0 plus 1, which is 1, over 0. And the natural log of 1 is equal to 0. So this results in 0 over 0, or something that we could use L'Hopital's rule with. So using L'Hopital's rule to evaluate this, I have the limit as x goes to 0. The derivative of the natural log of x plus 1 is the derivative of the argument of that logarithm divided by the argument. And then the derivative of x is just 1. So we now have the limit as x goes to 0 of 1 over, I meant to write an x there, x plus 1, which becomes 1 over 0 plus 1, which is just 1. All right, so now what I have, going back to this equation here, now what I can say is the natural log of y is equal to the limit of this function, which would be 1. And next, we can now say, rearranging this as an exponential, I have, it's the log base e, so the base of this exponential would be e to the first power is equal to y. So if y is equal to e, and this function right here was equal to y, then what I'm saying is the limit as x goes to 0 of this function y which is a constant, e, it works out to just e. So switching over to logarithms first certainly could help and get our answer. Another method is to use the calculator and use a table. So for instance, if I put in x plus 1 raised to the 1 over x. Oops. Oh, I got a divide in there, sorry. Raised to the 1 over x. And we'll use a table. So let me make sure my table is set up properly. Good. And I'm interested in values that are approaching 0 but not equal to 0, because if you notice, 0 gives us an error. So let's say like negative 0.1, negative 0.01, negative 0.001. And you can see that they're getting closer and closer to a value, about 2.71. And if I keep getting closer, it's not going to approach anything that is necessarily rational or easy to determine, but it is approaching the value e, which is 2.718. So that's what's happening there. All right, so then let's see what happens on the other side. So 0.1, 0.01, 0.001. That's also looking like it's approaching the value e as well. So we have the right idea and the right answer here. This limit is approaching